Welcome to our new lecture regarding soil consolidation. Last week we studied about soil consolidation and we saw how the consolidation occurs in the field. In the field, when we have a fine-grained soil and a load is applied on top of it, this saturated fine-grained soil under the action of the load tries to get compressed, but because the water that is entrapped between the voids cannot leave the soil very easily, so the settlement or the compression takes a considerable amount of time. And this phenomenon is known as soil consolidation. Now, we replicate the whole thing in laboratory conditions as well. And how we replicate the same thing in the laboratory conditions, in order to replicate it in the laboratory conditions, we replicate this field scenario in the laboratory conditions by first taking a soil sample from this clay layer, and the quality of that soil sample is that the main basic properties of this soil sample remain intact. It means when we take this soil sample out of the soil, the natural moisture content, the density, and these basic properties, we take the sample in such a way that these basic properties remain the same even out of the soil. So this is why we call this as an undisturbed sample. Now, this undisturbed soil sample is then placed inside a metal ring, and this metal ring, it is fixed inside a metal ring. I hope this would have got a little clear to you from the video that I shared last week. So once the soil is put inside this metal ring, then it is placed inside the consolidation apparatus. So this chamber, which is known as a consolidometer or an oidometer, we put this ring inside at the center of this oidometer. So you can see the sides of the ring here and here with the soil inside. Now, it is placed inside this metal ring in such a way that there is a porous stone at the bottom and a porous stone at the top. What does this porous stone at the bottom and the top does? It actually is replicating the field conditions, because you can see in the field at the top and at the bottom of the clay layer, there is a pervious layer. Now, in order to reproduce the same conditions, we put porous stones at the top and at the bottom. Now, it is very important for you to understand this, that what happens when we have a pervious layer at the top and at the bottom. You see, the thickness of this clay layer is generally called length of the drainage path, represented by capital H. Now, this length of the drainage path, when we have a permeable layer at the top and a permeable layer at the bottom, what happens is we assume that when we apply the load at the top, now the water which is here, some of the water can leave this clay layer from the top, and some of the water can leave this clay layer from the bottom. So if I ask you, what is the length of the drainage path in this case? The length of the drainage path would actually become half of this layer. Why half of this layer? Because the water which is present maybe at the center would require to travel only half of the thickness of this layer. So length of the drainage path would be half of this layer. This is known as two-way drainage. Now, what we mean by two-way drainage is, by two-way drainage, we mean that the water there is a pervious layer at the top and a pervious layer at the bottom, and because of this, the water which is saturating this clay layer can leave this clay layer either from the top or from the bottom. So in this way, this is called two-way drainage, and in case of two-way drainage, the length of the drainage path is half of the thickness of this clay layer. The same rule applies on this scale, on this soil sample as well. Now, in this case, again, it is going to be two-way drainage, because half of the water can either escape from the top porous stone or it can escape from the bottom porous stone. So in this case, it is again two-way drainage, and the thickness of and the length of the drainage path would be equal to half of the height of the soil sample. On the contrary, it is possible that this clay layer does not have any sand layer at the bottom. Maybe there is a continuous clay layer, or maybe there is a rock which is impervious at the bottom. So in that case, you can see there is only one direction for the water to escape this clay layer, and that is through the top. In that case, that is known as one-way drainage. And in case of one-way drainage, length of the drainage path is equal to thickness of the clay layer. So important for you to remember are these points, that in case of two-way drainage, the length of the drainage path is equal to the half of the clay layer thickness. And in case of one-way drainage, length of the drainage path is equal to the thickness of the clay layer. Okay, so coming back to our consolidation apparatus, you can see by filling this oedometer with water, we have replicated the same field conditions in the laboratory. Now, the same field conditions have been replicated here in the laboratory. So what we do is we apply certain load at the top, although we apply a point load, but this point load gets converted into area load because of this top loading pattern. So we apply a load on the top, and once we apply a load on the top, deformation starts occurring, but we know that consolidation is a time-dependent phenomenon. So as soon as we apply the load, we start noting the time by means of a stopwatch, and we start taking readings by using a dial gauge. So we take readings of deformation at load number 1. We take readings of deformation at regular time intervals, for example 1 minute, 2 minutes, 4 minutes, 10 minutes, and so on. And we keep on taking those readings for the first loading increment till 24 hours. After 24 hours, we apply the second loading increment, and for the second loading increment, we once again start taking the dial gauge readings at 1 minute, 2 minutes, 3 minutes, and so on up till 24 hours. In the same way, we keep on applying the loading increments and keep on taking the dial gauge readings. So this is the generalized procedure of the consolidation test. Now, one thing that we discussed in the last class as well, that while we are performing the consolidation test, there are basically three main observations that we are taking. What are those three observations? The first observation is the applied load, or you can say the applied pressure. The second observation is the time, and the third observation is the dial gauge reading. So basically, there are just three observations that we are taking: the applied pressure, dial gauge reading, and the time at which those dial gauge readings are taken. Now, by using these three observations, we are going to make further calculations in this, in case of consolidation test. Now, before we go into calculations, just to give you a quick review, you might remember we discussed this earlier, that when we talk about consolidation, we are only interested in finding these two things. We are interested to find either the magnitude of consolidation settlement or the rate of consolidation settlement. Means what is the total settlement that can occur because of consolidation, and secondly, at what rate or what speed this consolidation can occur. And we also studied this thing that the magnitude of consolidation settlement is measured in terms of an index which is known as compression index, represented by C subscript C. And the rate of consolidation is represented by means of a coefficient of consolidation which is represented by C subscript V. Okay, so we took three observations. We took pressure reading, the dial gauge reading, and the time reading. Now, what we can do to find out CC and CV. So you see, if our main objective is to find out the compression index and coefficient of consolidation, what can we do to determine these two things? So our next discussion is only based upon these two things. So in today's class, in fact, we will see how this CV can be determined. And in next classes, we will see how this Cc can be determined. Okay, so by using the three observations that we have made, the pressure observation, the dial gauge reading, and the time, we can plot two different graphs. The first graph that we plot is a time versus deformation curve, and the second graph that we generally plot is a pressure versus deformation curve. The first graph is the time versus deformation curve, and the second graph is the pressure versus deformation curve. Now, what do you think? By using the time versus deformation curve, obviously it is going to be a graph. Now, from this graph, which of these two things we can find out? Now, as you might have guessed, because it is time versus deformation and the CV can be used to determine the rate of consolidation. So yes, by using this time versus deformation graph, we can determine the coefficient of consolidation. Because if we want to get an idea of the rate of consolidation, we need to know the time. If we don't have time in our graph, we cannot determine the rate. So by using the time versus deformation curve, we can determine the coefficient of consolidation. And then by using the pressure versus deformation curve, we can determine the compression index, Cc. But this pressure versus deformation curve is of some more use for us as well. There are some other parameters, for example, C subset R, which is called the recompression index. There is a coefficient of compressibility and coefficient of volume change, which can also be determined by using the pressure versus deformation graph. So our today's goal is to see how to determine CV. So we'll limit our discussion to this point number one here. And in the next classes, we will see how to use the pressure versus deformation graph. So in the previous lecture as well, we have seen that this is how the typical time versus deformation graph looks like. So this is the typical shape of the time versus deformation graph for any particular loading increment. Now, this is a very, very important point that many people miss, that this time versus deformation graph is generally plotted separately for each loading increment. It means you can determine the coefficient of it means you can determine the coefficient of consolidation separately for each loading increment. Okay, so this is the typical shape of the time versus deformation graph, in which the time is plotted on the log axis and deformation is plotted on a reverse scale. This graph generally has three stages distinctly visible from it. The stage number one, which is called the initial compression. Now, why this initial compression occurs is because initially when we put load on our soil, so because the top of the soil sample is a little loose, so that loose part causes some extra compression, and this is why the slope of the graph is a little different. Now, this second stage is actually what represents our primary consolidation or the main consolidation, and this is the phase in which the water expulsion from the soil takes place. And stage number three is basically the secondary consolidation, and this secondary consolidation is pretty much like the creep deformations in the soil. So this is the basics of the time versus deformation graph. Now let's see how we can use this graph for the determination of coefficient of consolidation. Now, for the determination of coefficient of consolidation, this graph can be used if we know this CV, by using this CV, we can determine the rate of consolidation and also the time of consolidation. There are basically two different methods which can be used for the determination of coefficient of consolidation, CV. The first method is called the Casagrande's log time method, and the second method is called the Taylor's square root of time method. Now, let's have a look at both of these methods one by one. So first of all, let's look at the Casagrande's log time method. Now, you might remember this is the basic equation that we have used for the determination of CV. So if our objective is determination of CV, and if we want to determine CV, we need to find out these three things. By putting in these three things in this equation, we can easily determine CV. So What do we need to determine? You remember this h is the length of the drainage path. Now h, which is the length of the drainage path, you had the soil sample with you, and in the soil sample, as I explained on the first slide of today's lecture, so in the soil sample, you simply measure the height of the soil sample, and if it is a two-way drainage case, this h will be equal to height of the sample divided by 2. And if it is a one-way drainage case, then it will be height of the sample. Then for one-way drainage, this h will be equal to height of the sample. Okay, then this t, you also know t is called the time factor. And for time factor, in the previous lecture, we have seen a couple of formulae which are used for the determination of time factor. If you don't remember those, I strongly suggest you to go back on the previous lecture and look at those formulas before going ahead with this. Okay, and this is time of consolidation. Now let's see what we can do for the determination of CV. So first step is that we draw two tangents at the bottom part of this graph. So we draw two tangents like this, as you can see. Once we have drawn two tangents, we draw a horizontal line, and this horizontal line represents U100. From the previous lecture, you might remember that U represents the degree of consolidation in any sample. So this horizontal line actually represents 100% consolidation. It means at this stage, 100% consolidation has occurred. The dial gauge reading, this is the dial gauge reading axis. So the dial gauge reading corresponding to this line, let's call it R100. Now, if we have done this, it means we know beneath this line is going to be secondary consolidation, and above this line is going to be primary consolidation. This is what from our discussion on the previous slide. Okay, so what is going to be the next step? So we have separated the secondary consolidation from the primary consolidation, but now our goal is to separate this primary consolidation from stage number 1. So how can we do that? So in order to do that, what we do is in this first part of the graph, we take any arbitrary point. We take any point in this first part of the graph. You see, this is the x-axis is of time axis. So let's take any time value. Let's call it t1. Once we take this value of t1, the next step is we take another time value, but this time value has to be 4 times t1. Means if this was at 1 minute, the next value has to be at 4 minutes. Again, both of these are arbitrary values. The second value actually depending upon the first one. So if this is T1, let's call the corresponding dial gauge reading as R1, and let's call the corresponding dial gauge reading of this T2 as R2. Next thing is, we want to determine the difference, the dial gauge reading difference between these two. Let's suppose this difference is X. We take the same distance X above, and this, where this, at this point, we call it as 0% consolidation. So this is how we can determine the location for 0% consolidation. And if we have determined the location for 0% consolidation, let's call it as R0. Okay, so this is the procedure for determining R0 and R100 on the deformation log time graph. Okay, so once we have done this, what next? So if we know the dial gauge reading or the deformation for 0% consolidation, and if we know the dial gauge reading for 100% consolidation, can we easily determine the dial gauge reading for 50% consolidation? Can we determine the dial gauge reading for 50% consolidation? Obviously, the dial gauge reading for 50% consolidation can easily be determined because that 50% consolidation would be lying exactly midway between these two, somewhere over here. So what we can simply do is the dial gauge reading for the 0% consolidation plus the dial gauge reading for 100% consolidation divided by 2, it will give us the dial gauge reading for 50% consolidation. And by this, we can determine the time required for 50% consolidation. Now, this time that we have observed, this time required for 50% consolidation is the time which we need to put into this equation. Now, this is the time which we need to put into this equation for the determination of CV. So, but what I mean to say is when we are determining CV from the Casagrande's log time method, we can determine CV by using T50, and T50 can be determined from this graph like this. And the last thing that's left is the time factor. And time factor from our previous lecture, if you remember, I explicitly told you to remember the value of time factor for 50% consolidation. This value is 0.197. So if you know the time factor, you know the length of the drainage path from whether the soil is one-way drainage or two-way drainage, and then this T50 you have obtained from this graph. So simply by putting all these values over here, you can determine the value of CV. And if you have determined the value of CV, you can then easily determine the rate of consolidation or the consolidation time. Now, the same procedure that I've explained to you, I have summarized here for you as well. So this is just for your convenience. It is the same procedure that we have seen. So the step number 1 is plot the deformation versus log time graph. Then R0 and R100 represents the dial gauge readings for 0% and 100% degree of consolidation. When you want to determine U100, first of all, draw two tangents at the bottom part of the graph, and where they intersect, cut the graph, and this represents dial gauge reading for 100% consolidation. For determining 0% consolidation, take any time interval. First of all, take an arbitrary time interval T1, then take a second time interval T2 in such a way that T2 is 4 times T1. And then whatever is the vertical distance between these two, move the same distance above, and this gives you R0. And R50 is simply midway between these two. So this is how we can easily determine the CV by using Casagrande's log time method. So this was one of the methods for the determination of coefficient of consolidation. Let's look at the second method, that is the Taylor's square root of time method for the determination of coefficient of consolidation. In case of Casagrande's log time method, we used 50% consolidation for the determination of CV. Whereas in case of Taylor's square root of time method, we use 90% consolidation, and we use T90 for the computation of CV. So what we do is step number 1, over here we need to plot the graph between deformation and square root of time. You remember in previous case, we had drawn a graph between deformation on the y-axis and log of time on the x-axis. But here we are plotting a graph between deformation and square root of time. The graph, if I draw the graph looks something like this. Deformation on the y-axis and square root of time on the x-axis. This is the typical shape of the graph. So step number 1 is to draw a tangent to the initial part of the graph. So we have drawn the tangent to the initial part of the graph. Where this graph intersects the y-axis, this is 0% consolidation. And the corresponding dial gauge reading represents the dial gauge reading for 0% consolidation. So this is 0% consolidation. Now, how to determine 90% consolidation? For this, let's suppose that this distance is x. Now, if this distance is x, obviously you are doing it on a graph paper. So if you are doing it on a graph paper, you can easily measure this distance. So whatever is this distance, increase this distance by 15 times, 15%, and determine 1.15x of the same distance. From this point, you can again draw the tangent to the initial part of the graph. So in fact, you can again draw a line to R0. So you can join these 2 points. So once you have joined these 2 points, wherever this second line cuts your graph, that is the point which represents 90% consolidation, and the corresponding dial gauge reading is the dial gauge reading for 90% consolidation. So this is how you can determine 90% consolidation. Now, a summary of the same method I have uh, written here for you. So project the step number 1 is project the straight line portion of the initial part backward to 0 times. So first of all, draw this line, project it backwards, and wherever it cuts the y-axis, call it as 0% consolidation. Take the reading as R0. Then determine the horizontal line, determine the horizontal distance x, increase it by to 1.15, and then from this point, draw a line back to R0. Wherever this line cuts cuts your graph, this is T90. So again, once we have T90 with us, we can again make use of the same equation as has been used before. But you see, previously we were using T50, so the time factor was for T50. But now we are using T90 here, so the time factor has to be for T90. So by using these things, we can easily determine CV. Remember, this is why I told you in the last class to remember the value of time factor for T50 and T90 because they are very frequently used in soil mechanics. So you simply, what you do is you replace the value of time factor here. If it is one-way or two-way drainage, you insert the value of uh, the H here, whether it is one-way or two-way drainage. This T90 you determine from this graph, and you get the value of CV. And lastly, a quick summary of what we have said it so far. So basically, we have seen 2 different methods for the determination of CV. We have seen that the deformation time plot can be used for the determination of CV. One is the log time method, and second is the Taylor's square root of time method. So what we do in case of Casagrande's log time fitting method, we make use of 50% consolidation in order to determine CV. We plot a graph between deformation versus log of time. And then in this equation, we use time factor for 50% and time T50 as we obtain from this graph. When we are using the Taylor square root of time method, instead of 50% consolidation, we use 90% consolidation here. And the graph that we need to plot is deformation versus square root of time graph that we plot. And obviously, the equation also changes from 50% consolidation to corresponding parameters for 90% consolidation. And lastly, just a quick tip for you that the CV that we determine by using this Taylor square root of time method generally gives a slightly higher value compared to Casagrande's log time method. So this value might be a little conservative to be used in the design. That's it for today. Thank you very much.